Hello everyone, welcome to this fourth lecture on radiation. The topics for this lecture is the cosine law of Lamberts and an introduction to the view factor. These topics are taken from the compendium on radiation. We will cover chapters 3.8 and 3.9 in this lecture. So in the last lecture, we were looking at the radiation between parallel and infinite surfaces. As we have sketched here, we had a surface 1 and a surface 2, and we were able to calculate the net radiative flux or the energy flux between these surfaces based on information on the thermal state of surface 1 and surface 2. So these two terms are sigma T 1 to the power 4, and the other one is sigma T 2 to the power 4 from Stefan Boltzmann's law. And these emissivities that we have below here account for the non-ideality of these surfaces. Of course, the more general situation, or a real situation, we have to consider geometrical effects in addition, because our surfaces are seldom parallel, and or typically not parallel at least, and at least they're never infinite. So a more general situation we try to sketch here. We have surface 1, which is vertical, and we have surface 2, which is at an angle. And the question is then, what will the net heat flux be between the surfaces in such a configuration? So we will consider diffuse reflection. So the theory that we will develop in this lecture will not work very well for polished surfaces, so take note of that. So we'll do this for diffuse surfaces. And on this diffuse surface, we assume that we have a small element, dA, so this is a small area, and this area will radiate with equal intensity in all directions. So this is just a starting point for the geometry. So our area on the surface is here, and this area is a diffuse surface, which is why we have radiation going in all directions, as opposed to a polished surface where it will only be reflected based on a specific angle. So we will now have an observer situated here. And this observer is looking at the surface dA based on an angle theta, which is defined according to the vertical line. So this is regular polar coordinates. The observer, as the observer changes his or her angle to this surface, you will see different things. Assuming that the disk that we have, dA, in green, is circular. If you see it from the top, you will see the circle effectively. If you move to theta equals 20 degrees, so something like here, the area will appear flatter. It will look more like an ellipse. If you go all the way down to 90 degrees, that is that you go here and look along the surface, you will essentially not see anything at all of dA, you will just see a line. So all of this depends upon the cosine of the angle that you are observing of. So we define this DAA as the apparent area. So an observer looking at DA from an angle theta will see a different apparent angle. So this should be a different apparent area, sorry. Different apparent area, DAA, which is equal to the actual area multiplied with the cosine of the angle that we have. So here we see if theta equals 90 degrees, as we just said, then cosine 90 is 0, and then we don't see any area at all, while if we have angle of 0, then we see the full area. So we will be doing quite a lot of geometry and trigonometry in this lecture to get hold of all the concepts. So we'll have to introduce some useful relations before we start on the actual physics. All of the discussions we will be doing in this lecture depend upon what we call the solid angle. Solid angle is called romvinkel in Norwegian. And the solid angle, we will use the symbol dW, is defined as sine theta d theta d phi. And you can visualize it by looking at spherical coordinates. And you are looking at a specific area on the surface of the unit sphere, which has a radius 1. So this solid angle is related to the area on the surface of a sphere at a specific distance r from the origin. So its actual definition is this. d omega is this specific area, DAS, divided by the distance at that point. As you may remember from calculus, the area of this on this sphere is actually r squared sine theta d theta d phi. Maybe you remember it, maybe you don't, doesn't matter. But then it is clear that if you put this into the definition, r squared sine theta r squared sine theta d theta d phi, and you divide by r squared, you get exactly this expression that we have here. So it is corresponding to a pathway on a circle in a 2D representation, but this is a 3D representation, so it takes into account both the d theta and the d phi angle. D theta is the polar angle, and d phi is the azimuthal angle. So theta here will still be the theta depending upon the angle at which we are looking at our radiation source here in the center. So we use this solid angle to define what we call the radiation intensity. And that's a new property. We will use the symbol capital I to describe it. And it's defined as the derivative of the radiative heat flux with respect to the solid angle. So change in heat flux per solid angle. So that's essentially how the flux changes depending upon what angle you're looking at your source from. In a general case, this intensity will be a function of the angle at which you are observing from. So we will continue a bit and see how this relates to the things we are interested in, which essentially would be the heat transfer rate Q. So if we consider the heat flux is always given as the change in the heat transfer rate per area, because it's going to be watts per square meter. And we have now seen that this apparent area equals to cosine theta of the actual area, right? So this is the definition that we introduced from geometry earlier. Now, since the intensity I equals d lowercase q dw, change in heat flux per solid angle, and the heat flux itself is a derivative, this thing becomes dw of dq dA apparent, essentially. And that gives us the expression that we have a bit further down here. I equals then this second derivative that we get here. We have d and d. But below we have then dA dw. So it's a second order derivative with respect to both the solid angle and the size of the area from which the radiation is emitted. As I said, this in general is a function of the angle itself. This formalism for the intensity is greatly simplified for black bodies. Simplified for black bodies. And for black bodies, we have what is called Lamberts' law. And Lamberts' law states the following. The specific radiation intensity, so that's I theta, is independent of theta. That means that I theta equals a constant. And we denote that constant by IB because it is a black body. So we're using the same notation as we have been using throughout the course so far. Everything with a subscript B refers to a black body. It's important to note that Lamberts' law also applies for gray diffuse bodies. So it has to be diffuse still. And if we have a gray body instead, we will just weight this black body intensity with its emissivity. As we have done for all other radiation sources so far. So if we have a gray body, we use epsilon IB. If we have a black body, we just use IB. Let's put it in gray. Good. The next point is to elaborate on the cosine law of Lambert. So if we look at the heat flux Q dash defined as dq over dA. That is, we are looking at the heat flux leaving the source. If we do this, then we can write the following. The second order derivative of the heat transfer rate, well, is still equal to the derivative of the flux with respect to the solid angle. And that equals to the intensity multiplied by cosine theta. So this essentially also follows from the definition that we had here. Just multiplying cosine theta up to the right-hand side. And this is, of course, then for a black body for which IB is constant. This equation is what we refer to as the cosine law, because the intensity, or rather say the change in flux per solid angle, is proportional to the angle at which we are viewing the radiation source. So this is essentially the whole framework. We will be using that to determine how much radiation hits us from a specific angle, which is useful with respect to the scope of this lecture, which was to treat a general situation where we have one plate which can be vertical and another plate at a given angle, right? So we have an angle between these plates. But before we go into those details, we will actually calculate what the value of IB is. IB is a constant, so we should be able to determine it by using mathematics. So what we will do is that we will consider the full hemisphere, or halvkule. If we consider the full hemisphere as we see here, of course, then the flux has to be given by Stefan Boltzmann's law, because Stefan Boltzmann's law gives us the complete flux of energy. The flux, as we know it, is sigma times the temperature, and that's then the temperature at this emitting source, to the power 4. And this is, as per usual, EB for a black body. So that's the total flux. Now, from the cosine law, we had dq dot d omega, or w, sorry, equals IB cosine theta. And then if you take this dw and move it to the right-hand side, we have an expression or a differential equation for the differential in heat flux, which is then a function of this intensity, or black body intensity, times cosine theta times the change in solid angle. And the solid angle we have already defined, so I'll change the color of this one. Solid angle we have defined as sine theta d theta d phi. Now we can integrate this over the hemisphere, and then we have to look at the limits for the integral, the angle phi, which is the azimuthal angle, so this one. That one will go from 0 to 2 pi, because we're doing the full circle in that plane. Whereas theta will go from 0 to pi halves, that's 90 degrees, because it is the angle from the top going down to the base plane. So it's this angle. IB is in this integral constant. So we can move it outside the integral. And we are then left with an integral of cosine theta, which comes from the Lambert cosine law, so it's this one. And we have the sine theta, which comes from the definition of the solid angle, and then we integrate it over d theta and d phi. This integral equals to pi. So and then we had moved IB on the outside of the integral, so the heat flux in total equals to pi times IB. Now, according to our argument a few minutes ago, this has to be equal to EB, which is the total flux as predicted by Stefan Boltzmann's law. So that means that the blackbody intensity, IB, equals to the emissive power, or the radiation flux from the blackbody, divided by pi, and we can write that as sigma t to the power 4 divided by pi. So now we have defined what this intensity is, which is of course useful. So now we will have a brief discussion on the effect of real surfaces, and that means then non-ideal values for epsilon. So for a real surface, we write that the intensity, which now should be a function of theta, equals to epsilon theta times IB. Now this epsilon theta is the angular emissivity, and that is a parameter in which we lump the angular dependency. So the angular dependency is lumped into this parameter. So rather than having an explicit sort of dependency in the intensity, we put it in a prefactor instead. We're free to do so. It simplifies the formalism quite a lot. We have here a quite complicated figure, it may appear. On the y-axis, we have epsilon as a function of theta. On the x-axis, we also have epsilon as a function of theta. And theta will then go from the top here, where we have theta equal to 0, to the bottom here, where we have theta equals to 90 degrees. And we will define then this epsilon theta as the ratio between the true intensity divided by the intensity of a black surface. So for a black body, the epsilon theta equals to 1. So that means that it's not a function of theta. And for that reason, it retains its value of 1, so it's equal to 1, independently of the angle. So that's how you can read this figure. For a gray body, the same is true, except that we have a epsilon theta, which is then smaller than 1. So we get this curve, which is here, where we still have the same value of epsilon for all angles. The brown curve that we have here, so starting here, that is for clay. For clay materials, we see that initially the angular emissivity decreases or is constant, and then for some value it starts to decrease. So when you're looking at it from a too large angle, the emissivity will decrease. This happens at around 55 degrees for this particular example. So that means that clay-like materials follow Lamberts' law closely between 0 and 55 degrees. The final material that we're looking at here is a shiny metal, which is this yellow curve. For that one, epsilon theta actually increases with theta. So this does not behave according to Lamberts' law at all. So you see it starts here at a specific value, then it is increasing up until we reach 90 degrees, where it has reached its maximum. So the point here, most important point, is that different materials behave differently. For black and gray bodies, Lamberts' law works perfectly fine, while for clay materials, like refractory bricks, for example, we will be able to use Lamberts' law up until some limit, while for shiny metallic surfaces that are then non-diffuse, it's not working at all. So that leads us to the final part of this lecture, which is an introduction to view factors. And the view factor will be a very practical tool that we will use to determine the net heat flux in a system like I've drawn here, where we have two general surfaces, A1 and A2, that are at some distance from each other and at some angles relative to each other. So the question is, what is the heat exchange rate between the surfaces A1 and A2, assuming that they are black bodies or gray, then we will just weight it with proper emissivity, but they are semi-ideal bodies with constant individual temperatures. So again, isothermal conditions. So we're back to where we started this lecture. What will be the heat exchange rate in this general setting? Of course, the critical point here is to identify the solid angle which the projected apparent area, A2, so that's the orange one, makes as it is seen from A1. So if you go back, A1 sort of has a field of view. How does this field of view observe A2? For that we need the solid angle. So the solid angle dW2 which the projected area dA2 makes with di1 is given in this expression. It is then the cosine of theta 2. So it's the actual area multiplied with the cosine of the theta 2 divided by r1, 2, which squared, which is the distance between the plates. Here. If we now consider the heat transfer rate from surface dA1 to dA2, we can then use the cosine law and find that the second order differential, remember this was a second order differential equation for the heat transfer rate, equals to the black body intensity multiplied with the angle theta, or cosine of the angle theta 1. Why theta 1? Well, because it is the radiation from dA1. So it's from dA1. This is so this is the following from the cosine law. Then we have to multiply this with dA1, because that's the area from which the radiation is emitted. And it goes into this dW2. So that's sort of representative of the area that we have, or that surface number 1 sees of surface number 2. So note the colors here. Everything here in orange refers to surface 1. This is the part of the radiation leaving the first surface, while this here that we have in green is how much of surface 2 is seen by surface 1, so to speak. We have the expression for dW2 here, so next step is of course to substitute. And we also substitute for the value for the intensity. So again, we have EB1 over pi. This is just IB. We have cosine of theta 1 dA1. And then we have substituted the differential in the solid angle, as we have defined already. Then we restructure our expression somewhat so that we get two differentials here at the end. And now hopefully the notation still makes sense, because we note that this is the second order differential of the heat transfer rate from 1 to 2. And that's why we have a dA and a dA here. Hopefully this makes sense intuitively. We are studying the heat transfer from surface 1 to 2. So that has to, I note that this is the actual heat transfer from surface 1 to surface 2, not the net heat transfer. It's the actual heat transfer from the first surface. That one will depend, of course, upon the thermal state of surface 1, because that's where the radiation is coming from. That is EB1, the black body radiative flux from that surface. It also has to depend upon the orientation between the surfaces. That means it should depend upon both theta 1 and theta 2, because they can have their independent orientations along some axis. The distance should also be important, or the relative distance between the surfaces. And of course also the sizes dA1 and dA2. So the formula appears to include all of the factors that should be of relevance. Now, if we want to determine the actual heat transfer rate and not just the double differential, we need to integrate over the surfaces in question. So that has to be a double integral. We need to integrate over A1 and we need to integrate over A2 of this double differential. EB1 is a constant, so we can move that outside the integral. And what remains on the inside, interestingly, is only a function of geometry. So it's cosine theta 1, cosine theta 2 divided by pi and multiplied with r12 to the power 2. r12 is the relative distance between the plates. And we have then the differential of the area 2 and we have the differential over area 1. We call this double integral di. Oops, sorry. We call this double integral di. So the heat transfer rate from surface 1 to surface 2 equals to the black body radiation flux from surface 1 multiplied with this double integral. Now if we do the corresponding calculation from surface 2 to surface 1. So 2 to 1. Of course, we will get EB2 instead, because it will depend upon the thermal state of the second surface. We would interchange the order of the integrals, so here and here, and also the order of the two cosine factors. But of course, we are free to change the order of the integrals, etc. That does not change the value of the integral. So we can actually rewrite the integral that we have here as this. And this is the same double integral as we had for the heat transfer rate from 1 to 2. So the only thing that changed is the energy flux, which depends upon the surface that we are looking at. So the next point is to compute the net heat transfer rate, and note then again that this 1, 2 sort of means 1, 2 or the net heat transfer rate. So this notation is used in the compendium. We compress it to 1, 2. So the net heat transfer rate between the surfaces equals to the difference between the heat transfer rate from 1 to 2 and from 2 to 1. The first one is EB1 times the double integral. The second one is EB2 times the double integral, so we can move the whole double integral outside and we just get the difference in the black body radiative flux. And that's it, actually. So based on these expressions, we will introduce a few definitions, or one single definition, and this is then our introduction to the view factors. So based on the expressions that we have just derived, we write that the heat transfer rate from 1 to 2. So originally that was EB1 times the double integral. Rather than writing it like this, we write it as A1, which is the area of the first surface, multiplied with this F12, and then multiplied with EB1. So it's the same EB1 as here. The only thing that we've done is to split this double integral into two factors, one containing the area and the other one containing this F12. F12 is defined in the following way. It is 1 over the area, A1. Same as we have here. And then we have this expression, which is the double integral that we have introduced already. This seems like or may seem as a strange definition, but we'll see in the following lectures that this is actually very, very useful to write it like this rather than considering the double integral instead. This F12 is the view factor. And with the specific order of the index, 1, 2, it is the fraction of A1's field of view, which is covered by A2. So how much of A2 is seen from A1's perspective? Correspondingly, we can also write a view factor for area number 2. So in this case, we will look at Q221, and then we will have A2 times F21, and then we keep the EB2, and again, this is equal to EB2 times the double integral. F21 in this case is defined as 1 over A2, and then again the double integral. In the next lecture, we will look at quite a lot of practical calculations where we use these view factors, and we will see that it is far more convenient to do that than to solve this integral for all imaginable geometries every time we need to do it. So it's a shortcut to treating real surfaces. And in the end, we have to remember that the relations that we have been developing, so the view factors that we will use in the next week, only apply to ideal or semi-ideal surfaces, that is, surfaces that are black or gray. And they have to reflect in a diffusive manner rather than a specular reflection. So that's it for today. Thank you, and you'll hear from me soon again.